ExploreNEOs results.
Yeah, hi everybody. Hello YouTube. So this is actually going to be two talks back to back. Not sure how best to do this, if we stop for breaks for questions after the first one or take them together, and they're fairly different in topic. Well, I guess we just wing it as we get there. I am a theorist, not sure how old school I am, because this talk is without any equations. But it does have cookies. But I have plots. Does that work? So everybody here knows what thermal inertia is, so I don't need to really introduce it. Here's how we see it if we look at the temperature distribution over the day, or rotational phase. And this is how we could easily tell it apart, if you could measure this. Really, what we do when we look at standard asteroids is we look at some limited range, and we use solar phase angle as a proxy for time. If I'm writing this here. So at face value, this still looks like it's easy to tell apart. But then there's roughness, and I don't really need to explain this to you, but it does make our lives harder. It changes absolute temperature scales. It changes the dependence of apparent temperatures with solar phase angle. It just messes up things in a number of ways. It gets worse when we get to the outer solar system, Kuiper belt objects or the like, when this is the type of phase angle range we can work with. Good luck with that. We cannot really get to the night side. But there, we get some nice temperature swings, especially here, when the sun rises. It's where this red line shoots up. But we can trick our way there if we look at eclipses. It's kind of like this thing, where we have binary asteroid system, and they rotate around each other. This is where the cookies come in. If the sun is there, this asteroid casts shadow on this one, and we have an eclipse. And if you look sideways, this at a large enough phase angle, we can actually see that. And we can see the temperature go down and back up in real time, much as if we could observe the night side. This, of course, has been done a number of times, especially on satellites. Our Earth's moon has been done as early as 1930, measured thermal inertia. But for asteroids, it has only been done in 2010 by Cruz. Oh, I actually have a video, if it works. Let's see. Oh, looks bad. OK, we have to do without animation. Doesn't really matter. More Spitzer data have been taken on two binary systems called 1996 FG3 and 2000 DPE 107. Those names may ring familiar for some of you. It's an interesting comic. And what my model to analyze those eclipses does, it's kind of cheating, because I only work with doubly tidally locked binaries. And here's where my cookies come in again. They rotate like this. So they always show each other the same hemisphere. That's like Pluto and Charon. They do that. And then in a body-fixed system, so here's where my two asteroids are, and the sun and the observer and all the rest of the universe rotate around them, we have one object. It consists of two different lobes, but in this body-fixed system, nothing really moves, except the outside world. This is what makes the modeling easier. And then I do take account of where we have shadows and what we can observe. And I will be discussing some mutual heating. Here's just a very small subsection of the thermal data I got on Patroclus back in 2006 when the observations were. This is with Spitzer IRS. So we used that thing as a spectrometer on Spitzer. It had 178 wavelengths that we could use. And I was really only interested in the absolute flux I got at each. So I used it as a 178 channel imager. It's not really what it's made for, but it worked. And so here, these error bars are only for one wavelength. That plot, really, I got the statistics of these error bars downsized by square root of 178. So it's not as bad as it looks. And really what it is we got two events. Patroclus is nice in that the two components are roughly equal size. So this thing casts shadow on that, and then half rotation period later, it's the other way around. Those effects are similar in size. It's nice. And I got thermal inertias out of it. And I don't really want to talk too much about the details there because this is 5 years ago. And you can read it up in the paper. But see what I learned from this. I had done a preliminary analysis in my thesis. It was just a year after the data were taken. It was in 2007, that's when it came out. And then my colleagues that actually determined the mutual orbit of this system kept working hard and kept refining the parameters of the orbit. It turned out that changed my results tremendously, much more than I expected it to. And this is one lesson learned I want to highlight here. You need a really good model of the mutual orbit to begin with, because otherwise you cannot plan when an eclipse takes place. But you need it to be even better if you want to make any sense of the data. The good news is that with the orbital model used in 2010, I got a reduced chi-squared in the expected range of unity. So I'm confident that this now actually makes sense. And before, the fit was a lot worse. But this was unexpected beforehand. Another new twist on Patroclus is that Buoy just got a paper out, was also presented at the DPS meeting if you were there, where they observed the same system in occultations. And if you're not familiar with what stellar occultations do, this is a copy from their paper, so I'm not taking any credit here. People look at a star, and boom, for some period of time it goes away. And that's because the asteroid is in front of it. And sometimes they see that twice. And that's because there's actually two asteroids that are close to one another. It's a binary. And getting many chords from observers at different locations, they actually get a very nice constraint on the projected surface at the time of the observation. So it's a very model-independent way of measuring sizes and shapes. It's limited to one point in time. So their size measurement was completely independent to the thermal one, of course, but it matches to within 6%. So that's enough to make me happy. I think I gave myself error bars of 10%. So okay on that front. But they can see that the shape of the components, shape of my cookies here, is very different from what I assumed back in 2010. And in 2010, I just couldn't tell. Based on the light curves, there were different possibilities. And I was hoping to have rerun my model by the time of this talk to see what that does to my thermal inertia result. But that hasn't happened. Luckily, I have a student who's going to do it for me, or so she says. She's working on it. So there is actually a realistic chance this is going to happen eventually. Oh, this is what I'm saying on this slide. Look at that. So another potential lesson to be learned is what the component shape does to thermal inertias. And I do not know yet, but I will know soon. Okay, away with Patroclus. Here's 1996 FG3, everybody's favorite binary system, I believe. It's a C-type, one of the probably more primitive C-types. It's a Europoid, to use this wonderful term. And it has a very low delta V orbit, so it's easy to fly to for a spacecraft. So it keeps getting mentioned as a potential target for spacecraft, and then those never get selected for some reason or another. I got Spitzer observations of this thing during eclipses in 2011. The problem there is that it's not such a nice, well-behaved cookie system where they do this Pluto-Charon doubly tidally locked thing. There's only singly tidally locked, if that is even a term. So the primary rotates faster than the secondary and the mutual orbit. But the secondary rotation and the mutual orbit are locked to one another. So this is more like Earth and Moon. Here's what my model predictions were, assuming spherical component shapes. And you really nicely see 4 different events. The first ones are where the small secondary does something to the primary. First one, I think, is where it casts shadow. The other one is where it hides part of it. So eclipse and occultation in my lingo. The third one is what I'm really interested in. This is where the secondary goes in total eclipse, hidden by the primary, but it's still visible from Spitzer. And you see the thermal response depends very critically on thermal inertia there. The higher the thermal inertia, the longer it takes for the flux to go down. Then it stays low for a while. And the fourth event, again, not very interesting, is where the secondary is just hidden, geometrically hidden by the primary. Okay, that was the figure that was in the proposal at the time. This is the data. It's not quite like that, but you can quickly see that there is one fast rotation in there. This is people who have ever seen plots by Peter Pravec and Peter Scheirech will recognize this format. It's their Fourier analysis of the data. Most of what we see here is the rotation of the primary, and the rotation period actually matches the known rotation period. Peter can magically subtract that out, and then we're left with this. And this is actually similar to what we expected. Look here. The first event you see here on the left is the second one here, the very deep one. Oops, what am I doing here? The second one is what we want, and the third one, again, is one that we're not so interested in. The real geometry and eclipse depth doesn't quite match, but that's because the model of the neutral orbit has changed a bit since time of the proposal. So this is something we're now looking into to get into my binary TPM. So, and again, my model needs a doubly tightly locked system. FG3 isn't. So what do? I either change my model, or I change FG3, and I opt for the second option. Kind of cheating, if you wish. And I'm just throwing my idea at you, and I'm curious if anybody finds it really stupid. If so, please let me know. What I want to do is I take the real data and subtract the primary rotation, essentially, and then add a spherical or spheroidal binary primary back in, and give it a rotation period that matches that of the mutual orbit, not the fast rotation of the real thing. And then I take these massage data, and I run my TPM for a doubly tightly locked binary on it. That's the idea. And everything goes right, and the student gets a degree out of it. Isn't that nasty of me? It's only a master's degree, so even if it fails, you still get a degree. So I'm really curious what people in this room think about this. If this is completely crazy, or only mildly crazy, or actually viable. We can always discuss later. Beer helps for this type of discussions. And I promised another binary system that's 2000 DP107. Also one of the more famous ones. We got Spitzer data, but there the situation is that we don't have an orbit model that is anywhere close to good enough to model this. But this is going to be coming up over the next 2 years, or so we hear from my Czech collaborators. So just stand by. Going away from the real data, and I hope you can read LaTeX. This actually sort of is an equation. I must apologize, I guess. So we've seen this a number of times today. The skin depth is proportional to the time scale. And normally, when we look at the data we look at, that time scale is the rotation period of our asteroid. For an eclipse, that's not quite it. Here, the relevant time scale is the duration of the eclipse, and that is shorter than a rotation period by definition, and by a lot. So what this means is the skin depth that I'm probing here is a lot less what we would do that we would get using the normal method. So here I sample shallow. I sample the top layer relative to what we would usually get, a larger skin depth. And this is really nice, especially if you were to measure thermal inertia both ways. I would not necessarily expect to get the same result. Or I would if the regolith were homogeneous with depth, then we should get the same result. But if it's not, comparing these two results is going to give us some idea on how it depends on depth. And I think this is one of the few ways of getting depth dependence here. There's other ways, but this is one of them. Especially if we think that something fine and fluffy sits on something coarser, then the eclipse measurement should be lower. Well, we don't have the data yet to tell, but it would be really cute. It would be really nice if you had in the future. Especially for FG3, that is actually a realistic option because the thermal inertia of FG3 has already been measured, except not through eclipses yet. So this is going to be an interesting comparison to be made. So what I want you to take home from this is observing eclipsing binary asteroids in the thermal actually does work. You can get thermal inertias out of it. And this way, you're not confused by roughness effects at all. You just cancel out. Because it happens at constant phase angle. Didn't actually discuss this, but I think this is obvious. Roughness is the problem here. And this is a big advantage over the usual method. Modeling is relatively straightforward for doubly tidally locked asteroids. Think those cookies. That's an attractor state for dissipating systems, but not all binaries are there. Yeah, and I'm working on a cheat to make it happen for non-locked systems. And the other thing I want you to take home is that the digital orbit actually gives us large uncertainties, much more so than you would naively expect. And that's all for this talk. Oh, does anybody have a quick question here? Maybe it makes more sense to ask now.
Yeah, this is a really cool idea. So we've been doing this on the moon. Well, you mentioned actually that the first observations were in 1927.
Oh, is that true?
I think the paper was published in 1930.
Yeah, that's the one we're saying. Yeah.
Pettit, I think was
Pettit and Nicholson, or something like that. Yeah.
Anyway, but we're still doing that on the moon with the diviner radiometer and also with some ground-based observations.
Cool.
So one result that we've found now that we can actually map the eclipse cooling with diviner is that this upper fluffy layer, this low thermal inertia layer, seems to be much more uniform over the moon than the thermal inertia of the deeper layers. In other words, when we map thermal inertia on the moon using the diurnal temperature cycle, which measures tens of centimeters depth, we see fairly large variations of factors of 2 or so, depending on the geologic setting of those materials. Whereas this upper fluffy layer, which is about a factor of 5 smaller than, in thermal inertia than the lower layer, and this is the upper millimeters to centimeters. For
this is exciting. I wasn't aware of this.
That's much more uniform over the whole moon. And features that look very different in this tens of centimeter range look very similar in the few millimeters range. So that's just a comment, I guess, and maybe something to think about when you start looking at this.
Great. Hey, thank you. This is very interesting.
Sorry. How long you think to speak? You have a second part now?
Yeah.
How long is it? Because we have only...
Short. Yeah. Well, maybe we just move on. Or was your question quick or long?
It is.
Okay, I'll ask the short one. So related to what Paul was saying, so for the moon, the diurnal period is 28 days, and the eclipse period is like 3 days. Is that right? Hours.
Yeah.
Hours. Right.
Yeah. How long does an eclipse last?
Right. So for your asteroids, what are the relative time scales? I mean, what are the eclipse time scales?
For the Patroclus system, the whole orbit is something like 4 days. It's a really slow system. And an eclipse, I don't remember on top of my head how it lasted, but it was separate Spitzer pointings to get a few points across, so it was of the order of hours. So talking a factor of tenths, a factor of a few tenths difference.
Right, because there are other asteroids that we look at that have rotation periods that are that time.
Right. Mm-hmm. Yeah, I'm strictly talking about comparison on the asteroid itself.
It's time to go ahead,
All right.
otherwise.
This is even working off this.
A little more than 5 minutes.
Chances are. Well, so this is really just a little advertisement plug on 2 observing programs that I'm a part of. Both use warm Spitzer to observe near-Earth asteroids. Dave Trilling is the PI of both. And I'm Michael Mommert, Joe Hoare, and a number of other people, some in this room, are involved in one or both of them. So you've probably heard about ExploreNEOs. We took data between 2009 and 2011, got something like not quite 600 NEOs in 3.6 and 4.5 micron to measure diameter and albedo. What you may not have heard is that we recently got essentially a second version of this approved in the latest call, which is called NEO Survey. And we just started taking data. And it's a very similar thing, 600 NEOs to get diameters and albedos out of Spitzer observations, except now we only do 4.5 micron. Actually, it turns out that from ExploreNEOs, we never really used the 3.6 micron data. So the idea is to create a large and uniform catalog of NEO properties. So we checked what could be observable over the cycle, excluded everything that would be above that line because that means they could be picked up by NEO-wise. Didn't want to duplicate on those. Tried to focus on the smaller ones. And yeah, here try to make it efficient, kind of find where the curve bends over to get a trade-off between high number of targets, but keeping the observing time reasonable. Never mind too much about this. We were very careful not to duplicate previous surveys like our own ExploreNEOs, NEO-wise, or Akari. We tried to avoid objects that will be observed by NEO-wise, except we cannot really tell where exactly they will be pointing at any given moment. So there may be the odd accidental overlap. If it's just a small number of targets, we thought that's actually a good thing instead of rather than a bad thing because it gives us comparisons. We didn't want to waste time, essentially. Yeah, again, it's mostly technicalities. As high heritage ExploreNEOs, the observations really worked, except we got rid of 3.6 microns because we don't really need it so much. And we made sure that we always stay on target long enough to get appreciable movement. That way we can subtract all these vermin off the sky, stars, galaxies, that type of stuff. And yeah, the slide is not optimized for this audience, but we were going to get all sorts of cool signs out of it, of course. Our 600 targets, 32 could be dead comets, 107 are low delta V. If you apply cut at 6 kilometers a second, if you apply more stringent cut at 5 kilometers a second, we still get 6 targets. It would be extremely interesting to fly to dynamically. And what's nice is all our results go up on a public website in a matter of days, I think is what our goal is. Here's where the URL is. It's not quite dynamic yet. It has a result list there that is now, I think, 2 weeks old. But work is in progress to make it fully dynamic so that from data downlink to results on this thing, we should have only a lapse of a few days. And this is really all I wanted to advertise, because on the thermal modeling side, there's really not all that much to say. It's a single wavelength. It's neatum with a fixed eta, like we did before, like so many other people do. And that is it, essentially.
Any question about this second part, or some left question from the first one?
So you asked for some comments about your approach to FG3, about changing the rotation period, right? I'm not. I should be more familiar since I was stuck with you on the 2010 paper, but I'm not too. The main thing that the binary model does is it looks at the thermal re-radiation between the components, right?
No, it really actually ignores whatever photons bounce back and forth between the components.
Oh, okay.
I made a case how this is negligible because of the solid angles involved.
Okay.
It would be relevant. You could observe the night side of the component that does the shadowing. But we don't say neither are we particularly interested in it.
Right.
But the photons that come back from the night side of the shadower onto the shadowed side.
So what's the main effect of modeling it as a binary model as opposed to just using
well, I check for shadowing and for obstructions of the line of sight towards the observer. That's really the only advantage over the standard convex TPM that the model has. So I actually do this before. Since in the co-rotating frame, everything is just fixed. This is actually part of the shape model itself. For each facet, I check which other facet could be shadowing me. And this is something that is then checked at runtime. The sun is here, the observer is there. Is any of the potential shadows actually shadowing me? If no, just keep going as if you were a convex TPM. And if you're eclipsed, set the solar radiation to 0. It's really that easy. That's why I did it, because of a relatively simple change to the standard TPM. Yeah, and the thing why I made such a fuss about the rotation period of the primary is, if I subtract the flux out and then put it back in, you see, assuming that they have the same thermal inertia, they would have a different thermal parameter if the rotation period is different. And this is why I want to put it in at a rotation period. Otherwise, I'm inconsistent with my model. Of course, it's an assumption that the thermal inertia is constant over both components.
Okay, some good news for you. You can eat your cookies now.
Yay!
And the next speaker is Tanga. We'll speak about L-type, rare remains of the first asteroid generation. Yes, well,
sorry for leaving a mess here.
Yeah.
Most things are virtual than I anticipated.
Because the problem, I want to resist. Okay, so I have a pointer here. Yes. Okay, thank you, Alberto. And so I have no cookies. I have a very little, just one talk, in fact. I have very little thermal inertia stuff, but I brought in this room barbarians, which is should sound something exotic and I hope interesting to everybody, because this could be very interesting targets for thermal modeling too, with some specific challenges in this respect. So they were already mentioned in previous talks, so I don't want to spend much time in defining what they are, just a short recall. I will give you a census how many are known today, where they are hiding in the belt, why we think they have a peculiar composition, very rich in refractory inclusions. Sorry, I just to get rid of this cable because I will fall sooner or later. Okay. Then we are extending the search for them, I will show some preliminary results, the characterization of some specific objects, specific physical properties, something peculiar which we don't understand very well, and the challenge for thermophysical modeling in the end. So what the barbarian is, basically it's an asteroid exhibiting in the phase polarization curve an exceptionally high inversion angle, as I was told already by Alberto, by Maxime earlier today, and the deep minimum. So you can see here these two dotted lines basically define the domain of the usual behavior of polarization as a function of phase angle, and so where you expect to find normal asteroids, where all the asteroids are, with the exception of barbarians, which are very far from that. And I recall polarization is sensitive to surface structure, granulometry, and to composition through the refractory index of the materials. So this thing is telling us something which is difficult to model, as Alberto mentioned, about the surface of the objects, which is also related then to thermophysical properties. Okay, the prototype of this category is the asteroid 234 Barbara, so that's why they are known as barbarians, even if it's not the largest barbarians. No, it's just the first to be discovered by Alberto, published in 2006. Okay, so if we go through the literature, we find in 2008 more barbarians. This, in fact, is expanded car with more points than the Gilaton publication of 2008. And you can see here a variety of phase polarization curves with basically the same, around the same version angle, always well above 20 degrees for the 6 barbarians here listed. Just to remember why we have a negative polarization, which conceptually can seem a little bit weird. It means basically that in this domain, where we have the minus sign, the polarization plane is parallel to the scattering plane, which is kind of anomalous with respect to what you expect, which is the perpendicularity you have for positive values. So the transition between positive and negative passes through a zero linear polarization region here, which is called the inversion angle. So after the discovery of individual barbarians, which are fairly large asteroids, in fact, there was a specific investigation of one suspect barbarian family. So barbarians don't come alone sometimes. And this was the case of the family of Bosonia, which is a kind of high inclination family. I will show you where it is in the parameter, orbital parameter space later on. And there were 9 members that we observed at VLT, because some of them are pretty faint, and 7 of them showed this barbarian behavior. So the red dots here are referred to the normal asteroids, and the black and blue to the barbarian components of the family. So these 2 ones could also be interlopers of the family. Maybe they have nothing to share with the others. We have no spectra for them. So the current census, the current list of known barbarians is this, if I made no mistakes. And you can see here the size range of the known ones. That just recall that polarimetry is a high kind of difficult technique, requiring a lot of photons. So that's why you are strongly biased toward large bodies. And okay, these are the ones for which the barbarian signature is directly detected in polarimetry. Not many, okay? But the interesting thing, you can immediately see that they are spectrally very similar. In the BUS taxonomy of 2002, they all belong to the L, K, LD categories, so the spectra are not so different in the visible. And what's even more interesting is that if you consider the near-infrared extended taxonomy by DeMio in 2009, they all fall into the L category, at least for those for which the taxonomy has been determined by DeMio. So there is something related to the composition, to the mineralogy of those objects in the polarimetric signal. So where are they? Here you have the semi-major axis and the inclination, and basically you can find them nearly everywhere. So here the color dots are the L and K and LD types by BUS, and the circles are known barbarians. You have more suspect barbarians here. You have Anan group, which is suspect to be barbarian, but I will mention why they are suspect, because you have no direct polarimetry for many of these objects. Just notice that Barbara is here toward the inner ray belt, close to the U6 resonance. The Watsonia family is up there. Okay. I come back to this picture in a moment. So now, what's an L-type then? L-type are defined as having objects having a steep slope in the visible region, leveling out abruptly around 0.7 micron, and a gentle concave down curvature in the infrared, meaning that you have this small signature recalling presence of olivine probably, and then there may or may not be a 2 micron absorption feature in the near infrared. Okay, so there was a first interpretation based on the polarimetric observations by, namely by Alberto, starting for the first discovery. Very speculative possibilities was that very large impact craters or concavities on the surface could affect the distribution of the incidence and scattering angles, and so have an influence on the resulting polarization measured by a remote observer. Then the other possibility, which is certainly operating, given the similarity in composition of all these objects, shape probably is not one of the single possibility, but you always all take into account composition. And the idea, based on laboratory measurements by Zellner in 1977, is that you can have some mineralogical components that produce a high negative polarization, high inversion angles, and you can find them in a spinel, which is embedded in calcium aluminum rich inclusions present in CO3 and CV3 meteorites. For non-meteorite expert, I recall this is basically Allende meteorite, which is a very famous example. So this is spinel. There are different varieties associated to metals that can plug into the can go into the chemical formula here. So you can have chromium or iron inside, and the iron variety, which is called also arsenite, can have this exhibit this wide absorption feature at 2 micron. And basically, this is the only mineralogy that does not introduce other absorption features at other wavelengths that we don't observe in L-type asteroids. So that's why this is a good candidate for explaining the spectrum of L-types. But also, laboratory measurements show that polarimetry goes in the right direction for these objects. So here on the horizontal axis, you have the inversion angle, and in the vertical axis, the depth of the polarization minimum. So one of basic parameters described in this polarization curve. And Belskaya et al. In 2010 published this collection of laboratory measurements from crashed meteorites in the lab. And okay, you can see here the different symbols refer to different kind of meteorites. So basically, we are interested mainly in this region here. So Barbara is kind of around there. Okay, the asterisk there. Lutetia kind of intermediate. And if you get a piece of the alien meteorite and you crash it to powder, you reach this region here. If it is solid, so big pieces, you are toward the left. So the inversion angle is too small. But if you go to finer dust, you move to the right. You approach the region where observed barbarians are, even if you don't match exactly them. And no measurements in the laboratory is able to reproduce exactly those parameters at present. Just to show you a picture of what I'm talking about, this is a very big CIA inclusion of the what's called the fluffy type, which has not been melted. So it contains a signature of the grains, that very small grains, sub-micron level, that probably condensed in the the hot inner part of the solar nebula. And the meteorites containing the largest amount of these inclusions reach about 30% abundance in these inclusions. So this is the highest amount found sampled in the laboratories. And this is the most ancient material dated in the solar system, as probably you know, 4.568 billion years, okay? So we know nothing older than this. Okay, Raja and Gaffey back in 1984 took pieces of Allende and divided the calcium aluminum rich inclusions from the matrix, and they took spectra in laboratory in the near infrared that they were at the time they were not able to explain, as I told you, the presence of iron in the spinel, but they measured the presence of this deep 2-micron absorption band in the near infrared. Okay, different depth depending upon the sample, but anyway, it can go down very deep, and the metric is completely different. Brings a small signature of olivine in this region of the spectrum. So now, who made the best connection between CV meteorites, ancient inclusions, and barbarians was the Jessica Sunshine in 2007 and 2008 papers. And basically, she took the laboratory measured spectra of different type of CAA. So the unaltered fluffy type is called FTA here. Type B is something that has already been thermally altered, melted. So it's very different. It has a very different spectrum. And this is the flat spectrum, is the bulk Allende if you take everything together. Okay, so by combining these components, you can try to fit the spectra of barbarians. And here you have the different spectra acquired by at ERTF from well-known barbarians, and also some other objects which exhibit a similar spectral signature, but it has never been, as far as I know, targeted by polarimetry. Now, okay. So the result is pretty amazing, because in order to reproduce the spectral features in the barbarians, you have to include in your model a very high abundance of calcium aluminum rich inclusion, up to 30%. It is a strong enrichment, which is not found in any sample on the ground. And basically, it's the only solution that you have to produce this spectral feature here, following the conclusions by Jessica Sunshine and other collaborators. Now, I'm not really an expert in modelization of spectra, so maybe somebody could come up a certain moment with a better idea, a more common material to produce this feature. But up to now, I found no alternative explanation for that. So it's quite exciting. The idea that when we look at barbarians, we could looking at objects that incorporate the largest amount ever found of very primitive material. So CAA that formed very close to the sun, transported outward along with the chondrus that we can find in the same meteorites, with very modest thermal alteration, just a little bit, very short for a short time. All that is needed to transfer some iron into the spinal. Nobody knows exactly how this works, however. And the more ancient any meteorite sample available. It's quite a mystery. Now, when we say that this is the most ancient material, does it imply directly that we are looking at the most ancient asteroids in the solar system? Was this material created at the very beginning in the objects we observe today? Basically, we don't know exactly. But if it was just, for example, a coating layer on the surface of these objects, then it would be hard to find the families that are barbarians, because families come from the breakup of larger objects. And if you break up something that has a property related just to a thin layer, it's very difficult to transmit the same property to all the reaccumulated and fragmented family members. So we tend to think that this can be a property related to the bulk composition of the object. And an open problem is that these asteroids did not differentiate or melt, because these FTAs are primitive, are not altered by thermal processes. So despite a high amount of aluminum that is incorporated, so this could be object that could have differentiated at the beginning of the solar system. But we don't observe this differentiation. So now, based on this small sample, of course, it's difficult to answer to this question. So we started an observational campaign, which is still underway by spectroscopy, searching for the 2-micron absorption of a larger sample of L-type asteroids. We had to run specs for the moment. 18 candidate barbarians observed, several confirmed in the sense that we get the 2-micron absorption on most of the L-type asteroids we targeted. And but we have no direct polarimetric observations of them. So we are performing polarimetry in parallel. Alberto, Maxime, and other collaborators, we are using different telescopes. I just mentioned the two here on which we got time. This telescope in Nice is basically just 1 meter, but is available about all the time for asteroid observations. So we are using this polarimeter built in Torino for performing the measurements. And then a large photometric sample photometric campaign to increase the sample of shapes and rotation periods known, involving several telescopes around the world. And also using dense sparse photometry, as Josef Anush did in his recent publications. So just to show you an example, some asteroids for which you got a spectrum. Here you have this nice 2 microns absorption feature. Just a funny thing, so the variety of iron-rich spinel is also called ersinite. It's a mineral called ersinite, which was first discovered in a forest in Germany, in northern Germany, whose Latin name was Silva ersina. Now it is called Hearth. And so, and Ersinia is the asteroid that is bringing this mineral. So it's quite strange coincidence, but impressive. Anyway, these two objects here belong to another family, which is the Tyrrella family, a little poorly known family in the outer belt, but with a very strong, extremely strong signature of a spinel at the 2 micron. Tyrrella is out there, and if you look at the albedo of Tyrrella, is rather high in a region where everybody else is dark. So it's a quite interesting family to target for future studies on this subject. And then I will uncover the last column of this table, which was not, which was hidden before. We have a kind of open question, because if you look at the rotation period of these guys, well, at the beginning we were thinking to a coincidence, but there is nothing turning faster than 8 hours, which packs the single case. You have many, many periods without 12, 20 hours or 30 hours or more. So basically, these are not very, very slow rotators. You can have objects that turn in 100 hours, but these are really lazy rotators in some sense. And if you look at distribution of rotation periods, as a function of size, and just to get a slice where in the size range of typical barbarians we know, you get a distribution like this. The histogram shows here normalized to 1, to unit area, shows that clearly the peak of the periods that you expect to find is a little bit above 5 hours, between 5 and 10. Now, if I do the same histogram with the barbarians we know, plus some objects for which we detect the 2 micron absorption, I get this. Okay, this peak is not that far from it, but still it's about much higher, but very higher period. And here you have all this part, which is clearly not consistent with in abundance with the rest of the bulk of the distribution. So I see probably some perplexity in your eyes. I know what you're thinking, poor statistics. That's right. We are working for improving statistics. And the interesting thing is that each time we find a new period, Maxim is basically reducing the observations, and each time I ask him, so what's the period of this one? He always tells me 35, 24, 40 hours. So we are basically extending the sample, we are building the we are populating this area here. So we are not at all going toward the ordinary period distribution. So what's the link between the composition of these objects and their rotation? Is it due to collisional history? So this motivated, for example, the detailed study of Barbara from occultations and the light curves to retrieve its detailed shapes, showing that there are a lot of concavities. So this is an object that, if it is ancient, of course, it could have undergone an intense bombardment, so intense collisional activity. So it's not surprising it is so irregular. But the link to low rotation is still a little bit fuzzy. So we have other results in preparation for other barbarians for which we don't have occultations, but we will exploit the method Maxime illustrated to look for the signature of possible concavities. And also, we are trying to figure out an interpretation for this. For example, this Japanese group produced some numerical simulations showing that when you impact a rubble pile, the fragments that are flying away in non-catastrophic impacts, as cratering impacts, the fragments are flying away, bring away angular momentum, and the net result is you slow down your objects. So could this be one of the mechanisms acting on barbarians on a very long time scale? It could be. So certainly these objects are a little bit too large to fit into a York, be so effective on for these large sizes. And then I come to now close to the conclusion. We tried to compute some thermal inertia. So this comes from Joseph Anus. We tried to, as I showed before today, to fit a thermophysical model for known shapes of barbarians to derive thermal inertia. So here you get something around 50, 100, which is kind of small, but not exceptional. And in some situations it works. In other situations it doesn't work at all, because these are very slow rotators, so it's very difficult to derive a thermal inertia due to the fact that the amount of heat received by the body varies so slowly with time. So depending upon the orientation of the object, its shape, the process converges quite well or not. Usually we are in that situation on the right, so probably we have to target the fastest rotators of the sample to try to get more information on thermal inertia. We could constrain these properties related also to polarization. So conclusions, we continue to discover slow rotators systematically. The 2 micron absorption seems to be a widespread feature among the Mueller types, so a lot of spin-off out there. And wow, barbarian families are proved to exist. Some of them still wait for polarimetric measurements, but are very probable. And now, which are the implications? The unaltered inclusions imply early formation without differentiation or melting. So how did it happen? Following the last models of asteroid formation, very early asteroid formation, if we believe in the gravitational instability, for example, with the fast accretion of large asteroids, then these just could differentiate by incorporating a large amount of calcium aluminum inclusions. But still, maybe the incorporation of water could have prevented this differentiation. We don't know. For sure, in literature we found this this minor hydration signature on Anacostia observed by Rifkin, published in 1998. I'm not aware of many observable types in beyond 3 microns, so maybe I would be interested to know if in the sample from Macari there are some objects that could be studied for looking for hydration. I don't know of this category. Or maybe they did not contain at the beginning the classic abundances of aluminium-26. Certain meteorites seems to point in that direction, as if aluminium-26 was injected in a second time after the formation of the first objects. So a lot of open questions here. Where are the barbarian meteorites? We don't have samples like that in the labs. So they all fell a long time ago, maybe. These objects are very old, and the reservoir is empty today, or maybe they are simply too weak as material to reach the ground. Why barbarians rotate slowly, and which implication on the formation models? And I leave you with more questions than answers, I suppose. Okay, thank you.
Thank you very much. Marco.
Thank you, Paolo. This is very interesting. I don't fully get why you say the parent body shouldn't be differentiated.
Well, if these meteorites came from differentiated objects, this CA would have melted, and these are not melted.
But this you're talking about the CVs.
Yes.
But the CVs, there's a paper by Lindy Elkin-Talton that she proposes a model where the CVs are actually the crust of a partially differentiated body that has an iron core, then a kind of olivine mantle, if I'm not mistaken, and then the surface of this body is mostly undifferentiated.
Yes.
The reason for this is that the CVs have this there has this primordial magnetic field that can be explained with a dynamo, but not with the magnetic fields in the nebula, according to current models. And so maybe your guys could be the parent of the CVs.
Well, if it was a crust, we should not find the same barbarian character for the breakup of a family. Now, Watsonia is maybe a cratering event. Okay. But we have Inan, Tirella pointing all in the same direction. More verifications to be done. If really all the fragments are still barbarians, it's difficult to reconcile with just the crust. But of course, this has to be taken into account.
So, Paolo, this is more a comment than a question. We have done a survey, a spectroscopic survey using the 10-meter telescope, the GTC, on the Erigone collisional family. It's a primitive one in the inner belt, and we have found about 6 L-types there. So maybe they are interlopers, but still, I think it's interesting. They need for near-infrared confirmation for sure.
Yeah, L-type are distributed nearly everywhere.
Yeah. Maybe you're interested in this.
Yeah. I don't know the universality of the barbarian character on the presence of the microabsorption. Statistics are still too poor and biased to know if all the L-types exhibit this feature. How many of them exhibit this feature?
Okay.
L-type of the Meo or L-type of Bass and Beans? Because this makes some difference. That was a question by Javier.
Hidden here.
Regarding to the rotational period distribution you show, this comparison is with the sample of asteroid of the same diameter range?
Yes.
Or?
Yes, exactly. I selected the same diameter range to be consistent.
We're a little late. If there is just a quick question.
In your the collisional simulations, how do you create a rubble pile simulant?
Yeah, of course. This is a very tricky thing. These simulations are not mine, done by this Japanese group, which is using basically asteroids as assemblages of small spheres. And, they introduce some properties related to supposed mechanical properties of rocks, those conditions to provide a realistic restitution coefficients, etc. But of course, let me just anyway recall that this scenario is just the last one of an historically longer tradition of studies showing that collisions could slow down asteroids, starting from all the models of angular momentum splash, angular momentum dissipation by collisions that were mainly theoretical, and this is maybe the first to be numerical, but all goes in the direction.
Yeah, one of the reasons why I'm asking is that my student is working on a way of simulating more realistic rubble pile simulants using hydrocodes. So I might get you.
It would be interesting to know if there is an application to study the evolution of rotation periods and
one of the questions he hopes to address is this rotation period change
Yeah.
as a result of that, but using more realistic rubble pile simulants.
Yeah,
Maybe
yeah.
there's a connection.
We can discuss about that in detail.
Yeah.
Sure.
Okay, that would be nice to continue and make other comments as the time goes on. So we have to thank again speaker and go ahead. Presentation and M-type asteroids in the mid-infrared by Zoe Landsman.
That sounds quite strange. Do you have your presentation? PowerPoint?
I have it on a flash drive.
You can use mine.
I have to go get the flash drive.
Working? Okay, perfect.
All right. Okay, so I'm going to talk today about the M-type asteroids in the mid-infrared. We can learn about them from that wavelength range. So here's the outline of my talk. I'm going to go into just a bit of background about what the M-types are as part of that wonderful alphabet soup that is asteroid taxonomy. And then I'm going to discuss a bit the previous work that we've done, that I've done with my collaborators on the M-types at shorter wavelengths. And then I'll talk a little bit just about kind of where things stand with current interpretations of the M-types, potential analog materials, and then I'll get into what we can actually learn in the mid-infrared and the very, very preliminary results from what we've done there. So, I'm not sure why I'm missing some text right there that has magically turned itself white. That's very strange. But anyway, the M-types are, they're the moderate albedo subgroup of the X class. So in the Tholen taxonomy, Tholen 1984, the X class asteroids are those that have flat to red slopes and basically no diagnostic features in the visible. So this is what a typical X class asteroid spectrum looks like. And so unfortunately, there are a lot of meteoritic materials that look like this. So enstatite chondrites, iron meteorites, carbonaceous chondrites, and even the enstatite chondrites are all kind of similar. So the X class are broken down into groups based on their albedo. So the M types, just by analogy with the iron meteorites, are they're thought to be, or they were originally interpreted to be metal. So that's what the M stands for, because the M types are they have moderate albedos in the visible, and irons have similar reflectances. And enstatite chondrites are another, those are another possible early interpretation. But since then, we've learned that M types are complicated. So for one thing, it turns out that many of them have this 3-micron hydration feature. So that was originally done by Andy Rivkin, and there were some earlier papers, Lebowski and Jones, I believe, in the 90s. And then we've most recently done an updated study on that I'll talk about soon. But so it turns out that these things that maybe were metal have hydrated silicates on the surface, which is not what you would expect. And then more detailed studies with higher spectral resolution in the near infrared in the last 10 years or so, 5-10 years, have shown that most of the M-types actually do have weak absorption features around 0.9 and 1.9 microns, and these have been attributed to high temperature orthopyroxenes. But it also turns out that many M-types have high radar albedos. And so radar albedos suggest a high surface density, and then from that it's inferred that these have a high surface metal content. So it's kind of a weird picture of these things that have hydrated silicates and high temperature silicates and maybe a lot of metal on the surface. So what's really going on there? So just to talk briefly about the work that we did, I mentioned, oh, the internet wants me to log in. Okay, so I mentioned that that we did an updated study in the 3 micron region. What we wanted to do was to look at, with higher spectral resolution at that 3 micron feature, because it turns out that there's actually a bunch of different, I guess, categories or classes of 3 micron features, and that tells you a little bit about the nature of hydration on those asteroids. So in our first study, we looked at 6 M-types. We used the IRTF, NASA's telescope in Hawaii. And of that initial sample, we found evidence for a 3 micron hydration feature on all 6. I think at least one of those had been included in one of Andy Rivkin's papers as having a 3 micron feature, so we weren't surprised to see it in that particular asteroid. But several of them had not been looked at in that region, and one of them had been concluded to be, well, not concluded, but within the signal to noise available in that previous study was inconclusive. We determined that it did have a weak 3 micron feature. So the band depths that we found were in the 4 to 8% range, so not very deep. And on the next slide, I have a picture of that of those spectra. But what was interesting about this study was that several of them, well, what was interesting was we saw diversity in the shape of the feature. So as I mentioned, the shape of that feature tells you a bit about the nature of that hydration. So some of them had a sharp 3 micron feature attributed to hydrated silicates, hydroxylated silicates. One of them had a rounded 3 micron feature that's been attributed to water ice, or maybe goethite. And there are a few that have, well, you'll see some strange 3 micron features, but it's interesting that we see diversity. We also see evidence for rotational variability in asteroid 216 Cleopatra, which is one that everybody likes to talk about because it's very strange looking, well-studied asteroid. And then these spectra do show thermal emission longward of 3.3 microns that we investigated a bit as well. So this is, these are our spectra from the initial study, zoomed in on the 3 micron feature. All of these spectra have had the continuum removed, as well as the thermal component removed in this case. So this is just to show how, for instance, the 2 asteroids kind of on the ends of this top row have that sharp 3 micron feature. This one appears more rounded. So that suggests that there's different modes of hydration or different thermal evolution happening among these M-types. So these are the same asteroids, and this is like the zoomed out view. So here we have the full 2 to 4 micron region. And these have not been corrected for the thermal component or the continuum slope. So this is how they initially appeared. And then the red line is showing our best fit of the NEDM. So we just used a simple thermal model, the NEDM, for these, and we allowed the beaming parameter to vary to get our best fit. And we found beaming parameters in the range of 1.1 to 1.3, which is not hugely remarkable, but shows that there's some thermal inertia happening. And I'll talk about that more in a minute. The other thing is that, so I mentioned that M-types are typically red, have red slopes in the visible and near infrared, and we found that these had, that the continuum slope continued to be red out toward 4 microns. And so in order to get a reasonable fit of the NEDM, we had to modify it by sort of multiplying it by a red sloped line. Otherwise, there was just no way that it would work. So all that being said, where do we stand with the M-types? What do we know about them? And then I'll move into what can the mid-infrared tell us. So some potential analogs include, for those M-types that are inferred to have moderate or high metal content based on their radar albedos, these might be analogous to any these kind of meteorites. The irons, of course, are the classical M-type analog. But they could also be something like the mesositerites or any of the sort of strange high metal carbonaceous chondrites like CVs or even CRs or CHs. And some examples of asteroids that fall into this category would be 16 Psyche, which is considered one of the really good metal asteroid candidates, and 216 Cleopatra. So then there's another group that have a low inferred metal content based on their radar albedo. And internet is really insistent. So those that have a low radar albedo might be analogous to something like the enstatite chondrites, or even a recent suggestion at the last DPS was that simulated space-weathered olivine can actually look a lot like M-types and can have those weak 1.9 micron features. So that's good if you have radar albedos. And then this slide is just a bit of kind of wild speculation, but so okay, you have some analogs for M-types. Where did the hydrated minerals come from? This is not at all a conclusive list or anything. These are just ideas. So it's possible that that the hydrated minerals could in some cases be exogenic. We know Howardites have CM class, and there was this investigation from Dawn data of dark material on Vesta that's been interpreted as impacted wet carbonaceous chondrite-like material. So it's definitely possible that some hydrated material could be delivered by impacts to the surface of otherwise dry asteroids. Or even we know the moon has this sharp 3 micron feature that varies diurnally and has been attributed to implanted OH from solar wind interactions. So I suppose it's possible that this mechanism could happen on asteroids as well. Or we can consider the endogenic hypothesis, something, for example, CR2 chondrites. So the main issue with carbonaceous chondrites being analogs for M-types is that they're too dark. But some of them, so there are some strange CR2s that do have a more moderate reflectance in the visible. They do have weak silicate bands and red slopes and some phyllosilicates present. Again, I'm not a meteorite expert, so I don't know. This is just a possibility. And then Marco actually just mentioned during the previous question session this work by Lindy Elkins-Stanton, where was it the CVs? CVs could be, you could have a primitive crust on an otherwise differentiated object. So maybe you have M-types that are collisionally liberated iron cores with remnant primitive crust material on the surface. So again, it's all kind of wild speculation, but those are some ideas. Okay, so what about the mid-infrared? Well, we've heard a lot of really good introductions today to how thermal modeling can tell us a lot about the surface properties of asteroids. So I don't have to say too much about it, but we know we can get from thermophysical modeling, for example, diameter, albedo, and thermal inertia, which is a really nice indicator of surface properties. Additionally, emissivity spectra in the mid-infrared contain compositional information and information about grain size. So just some examples of how, of work that's been done in the mid-infrared on the M-types. Marco's 2013 DPS presentation, he showed that there are some high and low thermal inertia populations of M-types. And then there was a thermal inertia published for 16 Psyche that showed that it was quite high for a large main-belt asteroid. Psyche is, I think its equivalent diameter is close to 200 kilometers. So a thermal inertia of over 100 in the typical SI units is quite high. So that one's, again, a metal asteroid candidate. So, so the work that I've just sort of started doing, that I'm planning to do, is work I'm doing with the guidance of Josh Emery, is to do thermophysical modeling using Spitzer IRS spectra, 7 to 38 microns. And this is going to allow us to investigate all these properties that might tell us more about what these kind of ambiguous M types are. So we can look at thermal inertia, surface roughness, diameter, albedo, even the bolometric emissivity, and we can get information about composition from those emissivity spectra. And I think that it's interesting to, well, this is, I mean, it's interesting for all M types to do this kind of a study, but it would be really nice to be able to look at those that have been well characterized and see how these thermal properties play into, or how they relate to things like radar albedo and the presence of weak silicate features, the presence of hydration features, etc. So as I said, I just started this. So these are really preliminary results. I started on 16 Psyche, and I chose this one for several reasons. Because of the internet. Because
you can switch off the
let's try that. Okay. So I chose 16 Psyche partially because it's just very interesting. As I said, it's a really good metal asteroid candidate. It's currently the target of a proposed NASA Discovery class mission to metal asteroid. And the fact that it had been previously studied kind of allowed me to have a reality check, I guess, to start this work. So for now, I've only assumed a spherical shape. There's a shape model out there that I'll incorporate into the model later on. But depending on the value of the surface roughness chosen, I found thermal inertia in the range of 50 to 100, 120 in the SI units. And again, it's a little bit lower than the previous range, but it's consistent with the previous results, so that's good. And again, that is quite high for an asteroid of its size. And then this, again, this is preliminary, so I'm not super sure about this yet, but we do see an emissivity spectrum with a contrast of about 6%. And that's consistent, at least, with the presence of fine-grained silicates. I haven't done any kind of spectral modeling or anything to be able to say more about this. But it's just, it'll be really interesting to see how this plays out in the bigger context when I have more results, because with high radar albedo, high thermal inertia, it does seem like a great metal asteroid candidate. So it's interesting that it has features consistent with surface silicates. So it'll be interesting to see where that falls. Okay, so then just to wrap up, thermophysical modeling and spectroscopy in the mid-IR are really useful for asteroids that are ambiguous and difficult to understand at other wavelength ranges. And our plan is to continue to use these Spitzer spectra to better understand the M-type asteroids. Thanks.
I have a comment on the Matera type paper. I just like to remind that it was based on not very classical technique because we use interferometry.
That's right.
And so it's just, I believe it, but it's not being tasted.
Well, I think it's well, it's maybe it's I guess reassuring that it seems like that we're getting consistent results using more traditional method.
Hey, this is great stuff. I was wondering, in the spectra you showed earlier on in your talk, you saw these whopping bright thermal tails for, I think, 4 out of your 6 targets. And then 2 of them had much less of a thermal tail, even though they had very similar eta values. Why that is? They had like really high albedo or something?
So some of it was, yeah, so there is a bit of albedo variation between these asteroids. So I mentioned that I had to incorporate this slope into the NEDM in order to get it to fit. So some of them, have it's almost all the slope that you're seeing, and then it's a little bit of the thermal tail.
That's cool. I mean, like you said, these eta values are really high for large plane belters, so that's a piece of evidence supporting your case.
Yeah, and it will be it'll be interesting to see how to see if that's consistent with the results we get for thermal inertias.
There are other questions?
You mentioned Mike Shepard's observations of some M types, and at least my recollection was that he only found about a third of the sample that had high enough radar albedos to indicate high metal content, but also perversely, some of the high radar albedos were also objects known to be hydrated, so that we saw the 3 micron band in there.
Yep.
And having hydration and having metal and not having any FeO in the visible is really inconsistent. And so I wonder if you have any ideas of how to resolve that.
I'm sorry, can you repeat what you said about the visible?
So the problem we've always had with hydrated minerals and metal, iron metal together on the object is that if you have hydration happening, you're going to make iron oxide. And we would see that in the blue part of the visible spectrum, and that's not present here. Well, yes, but if it's an endogenic thing, if the hydration occurs when the metal is there, then we don't see the product of that. And that's been the inconsistency with Andy's work of the water band on things that don't have a drop-off in the UV, on the blue part of the visible spectrum.
Yeah, so I mean, I would say that those, I mean, this is, I guess this is probably the sort of easy go-to hand-wavy explanation, but I would say that asteroids that really do appear to be metal that have hydrated minerals would be the best candidates to have those hydrated minerals delivered by impacts or some other mechanism. Right. I mean, so it would be interesting to do, I mean, this is way out of my field, but to do maybe some kind of dynamical modeling to see what a kind of flux of, I don't know, outer belt material would be. And I guess the other thing that I've wondered, looking at these M types that have these really weak hydration features, I wonder, I don't know how much work has been done in other types of asteroids that are thought to be dry, like S types. Maybe there are S types that have these, you know, really weak 4% band depth hydration features. So maybe it is more common and it's just really difficult to detect. That's my naive answer.
I can also say that Gaia will observe systematically also the blue part of the spectrum. So this could be also interesting. So if there are not other comments and questions, we thank again the speaker. The next presentation this afternoon, Thermophysical Model of 1627 Ivar by Jenna Crowell.
Wonderful. All right, so I had the great luck of being drawn for the last talk today, so thank you for sticking through it and being here. So what I'm talking about is my progress for fitting a thermophysical model to 1627 Ivar, which you are now hearing for the nth time today. A little bit of background as to why we're doing this. What our group is wanting to study is the heterogeneity of the surface of these S-complex NEAs. So a lot of people ask me when I'm giving presentations on this is why Ivar? Why is Ivar so special? Given the fact that I've heard so much about Ivar today, I probably don't have to justify that to this group, but I'm going to do it anyways. So in 2013, it had a close approach to Earth, and we were able to get lots of data on it. And we are able to get different types of data on it. So our CWO group was able to get lots of radar data. So we had radar images and CW runs. And we also asked Brian Warner to get light curve fits for us. So we now have lots of our light curves for us, and we have lots of light curves now. We also got a lot of IRTF data, so this is reflected in thermal regimes, and so we have lots of data. And so the first thing that we wanted to do is, since our thermophysical modeling software depends so much upon the shape, we wanted to enhance on the current shape model of Ivar. So in 2004, Kesselinen had developed a shape model of Ivar that was based solely on light curves. Well, now we have all this radar data and light curves gathered around the same time period, so for the same epoch. And so we knew we could improve upon that. And so what you're seeing here in this movie is the original Kesselinen model kind of turning into the new model that we've now generated. So you can see it looks quite a bit different. And then it goes on to do the same thing for the side. But we have images of that in the next slide. So as I said, we have lots of data for Ivar. What you're looking at here is the orientation of the asteroid during the thermal observations. So this row along the top is the orientation of the shape model. And then the row right below it is how it's illuminated. So you're getting to see what part of the asteroid are you actually getting data from. And you may notice that down here at the bottom, there's a bunch of guys missing. The reason for that is the data has a lot of noise in it. And so it's not really been great at providing any constraints for developing the thermophysical model. So for the moment, it is kind of getting neglected. But you can see here that we have a wide range of viewing geometries, and we also have a wide range of phase angles here. So that's really useful. To start off, when we were trying to develop this thermophysical model, we didn't want to just throw all of the data in because it's sort of overwhelming. So we had to pick a good subset of the data just to start out with. And so what we were interested in was something that covered that wide range of phase angles. And something that you expected to be the same because you're looking at the same part of the asteroid. So to fit that bill, we have August and October here, that you're looking down at the top of the asteroid. The same portion of the asteroid is basically illuminated, but the phase angle is very different. So August, you have a phase angle of about 50. Whereas October, you have a phase angle of about 15. So they're very different. Also, in these days, like May, for example, you have many different observations throughout the night that maybe were separated by half an hour or so. And so this is also very useful as a diagnostic tool, which we'll see a little bit again later. We also threw in the September data because, again, you're looking at the same portion of the asteroid, so you expect to get similar results for that. So the next part is throwing this into Sherman, our thermophysical software modeling. And Ellen talked a little bit about that earlier, so I'm not really going into that a whole lot. Now, I realize this is kind of a mess of lines here, so give me a second to explain what you're looking at. For May, the May is going to be the green lines. And what I did here was I was plotting the best fit, so one that was like a perfect fit for the data. And this is thermal inertia here as the y-axis and albedo. Now the units for thermal inertia is just standard SI units. And so again, we're plotting the perfect fits, and what my goal was here is to create some sort of trend so I could see how the data were behaving. And that way I could go on to make predictions at maybe a given albedo, what would I expect the thermal inertia to be. And that would give me a good idea of where to begin testing this space. So like I said, the May is the green data. August is going to be the blue data. September is the one that it started curving a little bit earlier than the rest of the data. And so it wasn't really efficient to model it as being linear. And then October is this orange data here. So ideally what you want, for an example, with a crater fraction of 0.7, ideally what you want is there to be some point where all these things converge. And so keeping with the example of 0.7, it looks like everybody's converging around albedo of 0.34 and a thermal inertia of about 60. And that works very, very well for August, September, and October, but you notice May is nowhere around there. May is much more higher than the rest of the data. So it didn't really play nice with everybody else. And this is to remind you kind of what these things we're looking at. One of the things that I thought was kind of interesting and may have not been something I would have initially guessed to be the case is that these are so different. They have different slopes and they come in at different angles, and I wouldn't have really expected that initially. So it was very interesting to me. And so this is just zooming in on these plots here, and they have a little more data points because the thermal inertias do tend to curve at very low thermal inertias. So what I'm going to be talking about primarily after this is for diffraction of 0.7. The reason for this is if you look at this point of convergence here and the May data, the difference between those is the smallest in a crater fraction of 0.7 than it is anywhere else. In addition to that, you've seen in previous plots that Ivar is supposed to have a thermal inertia of around 100. And so if you kind of look where this is converging, you have a thermal inertia of about 50. And if you look at some point where maybe it's in the middle, it might get up to 70 or what have you. On the other hand, this crater fraction of 0.9 and 1 is much, much lower. So it's going to give us a lower thermal inertia, which is less than ideal. So you've seen this plot today. It should look pretty familiar. Since I had just started doing thermophysical modeling with this asteroid, this was very useful to kind of see where I should be ending up, like what kind of thermal inertia I should have. And so if I squish my asteroid into a sphere, I should have an effective diameter of about 9 kilometers. And so I should be right about 100, whereas that other paper said that they were getting, so that's great for them. And so then I went on to do fits. So the first thing I did was fit that point of convergence, so that point where you expect to find really, really good fits in the August, September, and October days, and sure enough, you do. They look really, really great. May, on the other hand, is a very poor fit. But if we increase that thermal inertia, we start to see that there might be a range of compromise where maybe we're not in the range of really great fits, but it's still pretty good. Like to me, this looked like pretty good results. And then if you keep increasing where you get to the point where May fits really, really nicely, you've now gotten to a point where your fit is much cooler than what the data is. So that fit should be a little bit hotter than what it is now. So if we go back to our compromise here, one of the things that's really interesting to note is, let's look back at the orientation of the asteroid. So here we're looking at the top, and those were pretty great fits. This is maybe a little bit cooler, but it's still okay. If we look at the May, what part of the asteroid are we looking at? So in the B set, we're looking again at the top of the asteroid, basically. We still got a little bit of that bottom and the end illuminated, but A is looking at a completely different portion of the asteroid. So that's really interesting that set is the one that's the most off versus everybody else. So could it be that there's something peculiar about the bottom of this asteroid? So if we look back at our inventory of data sets that we have here and look at, okay, well, what's another model that's looking at that same portion of the asteroid? We have this 29th September and this November set here. But remember, November is a really noisy day, so it's not very useful to look at. But 29th of September is very useful, and it's, like I said, it's still got that same portion being illuminated there. So if we do fits with it, we have very, very interesting results where the September 29th data and the May A data, the fits are too hot for both. So they're both off. Everything else looks great except for whenever we're looking at that bottom portion of the asteroid. And that has really interesting implications about the heterogeneity of this asteroid. So what I had shown here before, I had only gone to a crater fraction of 0.7. One of the reasons for that was in the beginning, I was believing that this was going to be my lower boundary because it looked like that September data was not going to intersect with everything else. Upon lots of further tests, I decided, okay, well, that's actually not true. So I don't really have a good lower limit at this point. So it could be maybe there's a point on the other side of that crater fraction that has a nice match. The problem with that theory, however, is that once you start decreasing that crater fraction, so if we're keeping everything else constant, we're keeping thermal inertia and albedo constant, and we decrease that crater fraction, you notice the data gets wider. So this is representative of the May data. And so you want the spread to be of a certain width. And so if we go back to what was a good fit that we just looked at a moment ago for May with a thermal inertia of 90, this is still a good fit, but it's getting into the upper range of that spread. So it's already getting to be a little wider than what the data really allows. So there definitely is a lower limit there, and we're already quickly approaching that. So there's not a whole lot of space there to play in. So then the much more interesting question is this telling us something about the heterogeneity of this asteroid? One of the things that Sherman allows us to do is play around with this by selecting certain facets and playing around with the properties there. So we might change the thermal inertia, the albedo, or the crater fraction, what have you, a combination of things. And so it would be interesting to go through and play with some of these facets, give them a different properties, and then go through and test it again and see if we can fit the data. But this is definitely indicating that there is a high chance that there is heterogeneity in this asteroid, which, again, to me is extremely interesting. And that's it.
Thank you very much. Are there questions?
Yes, I have a. No, it works. It works. It works. So I have a comment. This is very cool. And if you want more data, there is more data for this asteroid because Joseph's paper has a thermal inertia that is consistent with your results using WISE data.
Oh, wonderful.
But they are different wavelengths because they are more thermal. And there's also historical data from the ground that we took with Rick Pinzel and Alan Harris from the Keck, with the Keck telescope. So
yeah, that would be great.
So you can combine them, and maybe it could be interesting to uncover the question of Josh. Maybe because if you have pure thermal data, and you also use this shorter wavelength, maybe you can see emissivity variation. I don't know. It's just
yeah, that sounds wonderful. I definitely would be interested in that. Thank you.
Anybody else? Okay, in this case, we thank again. So tomorrow wear some warmer clothes because we will deal with icy bodies. And last for asteroids we have done.
So I have one news that tomorrow morning during the coffee break we will make an official picture of the meeting. So maybe we'll spend some more time during the morning, the coffee break. But we have plenty of time. Use 15 minutes more for the coffee break. Okay? So see you tomorrow. Thanks. See ya.